All right, hopefully you had a chance to stop and think about that. But the answer here is when we would expect deviations when things stop behaving like gases. And this all comes down to some of the assumptions that underlie what goes into the ideal gas law that we'll be looking at in more detail. So we would expect good agreement. Well, I guess let's talk about deviations first. We expect deviations at sort of places where things stop behaving like gases, right? Where as we tend to get towards lower temperatures, right? When we cool things down enough, even gases will start turning into liquids or even solids, right? If we think about dry ice or liquid nitrogen, right? Those are very cold temperatures. So at low temperatures, we get deviations. And also if we increase the pressure a lot. So if you increase the pressure enough, you can turn gases into liquids as well, right? And so that's where we're going to get deviations. So we would expect ideal behavior at the opposite of those. And the ideal gas law works really well for cases where we have high temperatures and low pressures. Now let's look into more why this is the case. What are the assumptions that underlie the ideal gas law? And this is something that's important in physical chemistry and physical models in general, is to know what assumptions are underlying the models that you're working with. And the ideal gas model, and we'll go over this in more detail when we talk about kinetic molecular theory next week, or in the next set of videos. But the assumptions that we have for the ideal gas law are, one, that the gas particles don't interact with each other. So basically they're just bouncing, balls bouncing around, and they, for the most part, don't notice each other. Now this could be either attractive or repulsive forces, right? So the atoms or molecules can pull on each other, or they can push each other away. Now obviously, eventually that's not going to be true, and if you have a high enough density of gas particles, they will start interacting with each other, and that's when you get liquids that form. The second assumption is that gas particles don't take up any volume. Now obviously this assumption is also false, right? Gas particles do take up volume, but under really low density conditions where you don't have very many gas particles compared to the volume of the container that you're working with, the volume of the gas particles can be negligible. And so when these assumptions break down is when we start getting deviations from ideal gas behavior. And when are these assumptions going to break down the most? They're going to break down the most at these conditions that we identified above, right? At low temperature and high pressure. At low temperature and high pressure, let's look at what's sort of going on in terms of if we have a box full of gas particles, if we have high pressure versus low pressure, what do these look like if we sort of draw a bunch of gas particles? So I'd like you to pause the video before I do this myself and draw some boxes and think about what would high pressure look like, what would low pressure look like. Okay, so high pressure is you're going to get a lot of particles packed into a small volume. So almost like it's starting to become a liquid, where you have a bunch of particles that all stick together. Whereas low pressure, we're going to have fewer particles in the same volume. So under the high pressure conditions, the gas particles are packed tighter with each other, and they're going to be that the volume of the gas particles is going to matter more, and they're going to interact more with each other just because they're closer together. We can also think about the same thing with temperature. We can draw a picture of high temperature versus low temperature. And here let's assume the pressure is the same. Right, so we have roughly the same number of particles. Draw 5. Obviously we have a lot more than that in any macroscopic gas sample. But at high temperature, these gas particles are on average moving much faster. So I'll represent that by very large arrows here. Whereas at low temperature, they're moving slower. Now, what does this have to do? Now, the particle volume doesn't matter so much here, but here it's the attractive forces. At high temperature, you have less time for the particles to interact because they're just zooming past each other. Whereas at low temperature, they have more time to interact, and so those attractive and repulsive forces will matter more.